Okay. Hello, my name is Jose Llorens. I'm working at the National Research Council in Spain, and I will be chairing this interesting mini-colloquium on the topic of topology and geometry control, Normalization of Nanostructured Metamaterials. So we have today a very tight agenda, and we are very lucky because the first presenter, the Professor Vladimir Fomin, will make an overview of the area so that it will be very easy for all of us to grasp what this is all about. And then next we will have a second invited speaker, also with a very interesting talk on the polarization of quantum dot dimers. Then a few contributed talks, and finally a flash talks on pre-recorded talks. So I think if Vladimir is ready, we can start with the with the presentation. Okay, please, Vladimir.
Good morning to you all. Thank you, Chair. First of all, I would like to highly appreciate the efforts of Maria Jose, Herman, and Jose Maria, who arranged this online meeting, invigorating the condensed matter division activities in these difficult pandemic times. I thank the co-organizers of this mini colloquium, Jose and Oliver, for inviting me. And you see here that this work was performed at the Institute for Integrative Nanosciences at the Leibniz Institute for Solid State and Materials Research in Dresden. This work involved many collaborations, and I would like to appreciate the collaborations with Oliver Schmidt here in Dresden and Chemnitz, Danilo Burger and Soren Lösch in Chemnitz, Roman Rezaev and Katerina Smirnova in Moscow and Tomsk, Russia, Alexander Dobrovolsky in Vienna, Austria, Rosa Cordoba in Zaragoza and now Valencia, Jose Maria de Teresa in Zaragoza, Herman Suderov and Isabel Guillamont in Madrid. This work was funded by DFG, Russian Fund for Basic Research, bilateral Germany-Russia research grant, and also by Coast Action nano-coherent hybrid devices. The outline shows that we will start with some motivation of these activities which were related to rolled up nanostructures. Then we will show the results on semiconductor, on superconductor nanostructures, which is the main topic of this talk.
Please, excuse me, Vladimir.
Issues are, please.
Sorry for interrupting. Can you share your screen? Because at the moment we can only see
sharing
your face.
1 second. No. I am now entering. Is it okay now?
find the green square at the bottom.
At the bottom bar?
Yes, green,
Yeah, I
green one. Find the
understand,
green
but
one.
I have already used it. Do you see my screen or not?
No,
No.
no, not yet.
So I clicked on share screen. Motivation, I will tell about mainly the superconductor nanostructures, and the key are topological transitions in superconductor curved nanomembranes and tunability of superconducting vortex patterns in micro and nano helices. The rolled up nanostructures were, in my opinion, one of the first attempts to realize new possibilities for experimental investigation of superconductivity in samples with curved geometries. Here in the left panel, you see a sketch of the method which is linked to using some ultra narrow membranes, for example, bilayer or 3 layers, which are put on a substrate using a sacrificial layer. And when this sacrificial layer is etched out, the strain which develops in the membrane due to mismatch of crystal lattices tends to deform this membrane, leading to the scroll. If the scroll continues, you can arrive at one tube-like structure or even radial superlattices. And in the central panel, you see an early example of such rolled up nanoarchitecture, which consists of a few windings with one of the layers being niobium, about 50 nanometers thickness. This is a nice nano tube, which is not carbon nanotube. It's made of another material. More recently, there were other attempts to fabricate such curved nanostructures, and I only briefly mention here the focused electron beam induced deposition or focused ion beam induced deposition, which are in the right hand side of this slide. And this was a topic of special session on Monday. Therefore, taking this nice experimental possibility to produce nano and micro structures of superconductors, we will go to the scheme of a characteristic structure, which is shown here. It's a tube, but it's an open tube. As you have seen from the previous slide, this is not a full cylinder. It's a cylinder with an opening, with a cut. And this cut may be used in order to attach contacts. Here they are shown semi-transparent. Imagine that such a tube is put in a magnetic field, which is orthogonal to the axis in the very first slide. And then we will send a transport current through the contacts which are attached to the banks of the slit. That is, in this figure, the current enters from the upper contact, then travels over cylindrical surface and leaves from the lower contact. The transport currents flows orthogonally to the axis, and in the next slide, in the next panel, you see that in such a complicated geometry, two sets of screening superconducting current develop. One set in the upper part and another set in the lower part. As distinct from a planar structure, we have here two sets of this connected superconducting screening currents, and this certainly will influence tremendously the properties of a superconductor in such a structure, as we will show in the next slides. The theoretical method I will indicate only very briefly. We were using the time-dependent Ginzburg-Landau equation, and it is supplemented with Poisson equation in order to take into account the scalar potential. The boundary conditions are absence of normal superconducting current on surfaces where there is no contact, but where there is a contact, we are using this transition region between superconductor and normal contact. So the transport current is introduced via the current in the contact. In very recent effort, we added also the lowest equation for the normalization of the magnetic field. We will show what happens of it. These are earlier efforts of estimating the state of superconductor, and depending on the magnetic field through the structure, there can occur vortices, as you see in the first picture here, or chains of vortices if you increase magnetic field, or even double chains of vortices in the third slide, in the third panel. I think here, okay, what happened? Okay, can you hear me?
Yes.
Okay, in the left-hand panel, we see here a surface of a cylinder where one vortex, upper vortex, flows from the right to the left and lower vortex from the left to the right. In the right-hand panel, we see a normal, typical situation for a planar film where vortices flow one after another, and you see now a video. They go in one direction. The motion of vortices in upper and lower half winds are correlated, and this is a fast consequence of the complicated topology of screening currents. This comparison can be continued to higher magnetic fields. In the upper part, we have a planar structure. In the lower part, we have a cylinder. There are.
Excuse me, Vladimir.
Yes.
Yeah, I only see the PowerPoint program open, so the slides are not running or any video is. We are seeing slide 7.
Okay, it's not important whether you can see a video. I am now at slide 8.
Yeah, but we are watching slide 7, so it seems that the screen is freezed, or at least.
Okay. Slide 7. Now let's go to slide 8. Next one. Can you see?
No,
it's not in presentation mode. You can choose the presentation mode.
No, I mean, he clicked on presentation mode.
I am in presentation mode. Okay.
Yeah, but for some reason, Zoom is not broadcasting. Now, no, not yet. Now we can see slide 8.
And now I go to the presentation mode as it was from the very beginning.
No, it's not working for some reason.
Then I will return to the normal mode. You see now the slide number 8?
Yes.
Okay, I am very sorry, but I will go now.
No, of course, please.
Okay. Typical characteristic times of the motion of vortices, which occur very strongly dependent on the curvature. And you can see from this slide that for larger radii, the characteristic magnetic field, for example, when you have only one vortex in a half turn, will be increased by a factor of 3 when reducing the radius by a factor of 4. You see here radius 800 nanometers, here 200 nanometers, and the typical magnetic field was increased by a factor of 4. Here in the inset is very interesting typical dependence of what happens if you roll up a planar membrane into a tube. You will increase the characteristic magnetic field as well as the critical magnetic field by a factor of 3. But I go now to the next. These properties can be controlled by introducing inhomogeneous transport currents by splitting contacts, what also will influence the characteristic times. What will be if we increase magnetic field? At a certain magnetic field, there should be a transition from one chain to 2 chains. And if the current is not strong, transport current, this takes place via bifurcation, as shown here. So in some part of the tube, there is only one chain. in some there are two chains and there is a transition. But this is only when the magnetic, when the current is not so strong. Our recent calculations, taking into account magnetic field renormalization, show that the nature of these vortices is different, dependent on the on the distance between the upper and lower parts of the structure. And here, if this distance is large enough, these vortices practically do not feel each other. They are too far from each other, as is shown in this figure. But if these parts approach to each other, the vortices try to feel each other, try to form one vortex line as expected, but nevertheless, due to Magnus force, which flows through this structure, like in the tube, they nevertheless are separated, as is shown in this figure. And now I approach one of the key elements of my presentations. Recently, we considered a similar structure, but in the conditions when there is a strong transport current. You see here a main topological difference between a planar structure and a tubular structure. In tubular structure, the screening currents form two disconnected loops. In a planar structure, a single loop. If we go into more detail representing what the parameter, its phase and currents, we will see that the planar structure reveals a set of vortices, and if you increase magnetic field, a phase slip enters. But in this case, we have three loops of screening currents, one of them around the phase slip. And in the case of a tube, we have two sets of vortices inside the loops. Now we enter a regime of higher currents. If we have a certain magnetic field, it's 6 millitesla, we have such a picture of moving vortices, which is confirmed by the estimation of change of the argument around this topological defects. Now we increase the magnetic field twice. And here we must have already almost two chains. And this is again supported by calculation of the phase. We can estimate the winding number for every defect. But interestingly, a transition between a regime of one chain to two chains is absolutely different. This is magnetic field 10 millitesla. If we wait till the transition from initial state finishes, we see here a picture which is practically does not change. It resembles a phase slip in the center. But what is behind this phase slip? And now wait a little bit. This video is slow intentionally in order to show you what happens inside of this phase slip. You see the phase introduces in many places phase defects. which are then disappearing. Then again, they appear on the central line opposite to the slit. Then they move and disappear. In the next slide, I will show what is behind this. If we look here at the winding numbers of each of these defects, which we saw in the previous slide, one of them is vortex and another is anti-vortex. And they move over this locus of their nucleation. Naturally, a vortex moves to the right until it meets an anti-vortex of the next pair and annihilates. An anti-vortex moves to the left until it meets a vortex from another neighboring pair and annihilates. But the vortices and anti-vortices are now occurring with very high speed. So the typical time of life is 10 to the power minus 15 seconds, while for vortices it's 10 to the power minus 11. So these vortices and anti-vortices move very fast. Because of that, if we calculate the voltage induced by the moving vortices and anti-vortices, as shown here, in this window of magnetic fields where this phase slip occurs, we see a clear peak. And this is peak, this peak for the niobium tube with parameters which are shown here. I hope you can see them. This peak is threefold. When we further increase magnetic field, so we can enter the double chain regime, this generation of the induced vortices goes back to the origin due to moving vortices in the upper and lower turns. And still at higher magnetic fields, this motion becomes faster, but in this case, these are moving vortices. What is still interesting here in the central part, that in place of two loops of screening currents, when this transition period occurs, we see another two loops, and just in between of these additional loops of screening currents, we have a locus of the formation of vortices and anti-vortices. So they are in the middle. A topological transition here is confirmed by the fact that we have now more disconnected loops of screening currents in the system. I must rush now. Similar calculations were performed for other material, for tin, and then the same peak occurs at lower temperatures shown here. So it's all material dependent, but robust. Taking into account that my time is almost over, I will very briefly go to the micro and nano helices which were fabricated both by self-rolling and by ion deposition. The examples are shown here. And in these structures, as you see here, in the case of magnetic field orthogonal to the axis of a nanohelix, you see screening currents flowing in multiple windings of a helix in the upper and lower parts of them, so that we can expect even more complicated pattern of vortices. And this is indeed confirmed by calculations of distributions of vortices first in quasi-stationary state. Depending on the magnetic field, we can arrive at incommensurability if there should be such a number of vortices which cannot be divided by the number of half turns, then these vortices may occur in different places. The geometry of nanohelix significantly influences the pattern of vortices. Here we have in every half turn maybe 4 vortex stripes, and here 6. Depending on the geometry of a spiral, we can have different dependence of average number of vortices on the widths. For sparse spiral, it is sublinear. For dense spiral, it's superlinear. But what is interesting here for the future, if we calculate the dynamics of these vortices, then this characteristic times, time of flight and time of nucleation, is different in outer half turns and in the inner half turns. So the nanospiral behaves differently in different places as concerns the dynamics of vortices. And this brings us already to the last point of my presentation. It's experimental detection of shelves in the resistance versus current characteristics in such tungsten carbide superconducting nanoarchitectures which were produced by focused ion beam deposition. There are a few steps if the measurement is just on 2 windings. And our calculations here, which provided some interpretation to this experimental observation in some nanohelices. Here it's 1 Tesla, here is 2 Tesla. Suggests the following scenario, that when the transport current is not that far, we have some distribution of the parameter according to the inhomogeneity of the magnetic field, which is very strong in this system. At higher magnetic field, there are even vortices, as shown here in the lower panel, but they do not contribute too much to the resistance. If we increase the transport current to a certain value, they develop phase slips in some windings, and certainly these phase slips induce voltage. In other way, they produce dissipation, and this is seen as a first shelf in the resistance current characteristic. If we further increase the transport current, these phase slips develop in more extensive regions, practically in all windings, but there are still some regions where magnetic field is tangential to the nanohelix, and therefore we arrive at the second shelf. And at still higher magnetic, still higher current, practically the whole nanohelix is already normal, and we have the finish of this superconductor to normal transitions. Depending on the time, dear chair, how much time will you give me? Hello?
Sorry, Vladimir.
Jose?
Yes, it's like two more minutes.
Okay, wonderful.
Directly to the next presentation.
Occurrence of these phase slips is obtained again on the basis of our theoretical modeling, but when in some windings the phase slips occur, even narrow, they will lead to heating, and therefore we suppose that this phase slips due to heating will spread over the respective half winding. But as you remember from one of the previous slides, these effects are inhomogeneous with respect to the number of half winding. Therefore, in some cases, the half winding remain superconducting. I think this will be practically my last slide, which shows that there is a significant difference between the structure of phase slips in a planar structure. These are 3 lower panels, and in a nanohelix, where this interplay between the confinement of screening currents and creation of vortices is dominant. I think at this point I already must thank you for your attention and attract your attention to the possibility to contribute your work to our special issue of applied sciences on the topic of the present mini-colloquium. That's all.
Okay. Thank you, Vladimir. Thank you very much. I'm afraid we don't have time for questions, but you can type them in the chat room, and I'm sure Vladimir can address you along the morning, or
yes, sure.
Have a private presentation, chat, sorry. So thank you very much, Vladimir. Can you please stop sharing your screen? Thanks. And now we move to the next presentation, the next invited talk by Professor Kim from Busan University in Korea. So it's all yours.
Okay. Okay, can I start?
Yes, of course.
Yes, yes. First of all, I would like to thank Professor Vladimir Fomin and organizing committee for inviting me here. Nice online conference. And my talk is about laterally coupled quantum dot. And I'm interested in polarization anisotropy, and I want to control the polarization anisotropy by using optical polarization. That's the key idea of my talk. It's very simple. Okay, so coupled quantum dot is a bit old issue. It was proposed back in early 2000 and for the building block of quantum manipulation. And initially, vertically quantum dot was proposed. If the distance between 2 dots is, for example, several nanometer, tunneling induced wave function overlap, and the symmetric electron bonding state and anti-symmetric anti-bonding states can be formed. And the distance can be controlled by changing the thickness of barrier between two dots. And then theory and experiments can be compared. And if you want to study optically, for example, exciton, you have to consider not only direct exciton, but also indirect excitons, which consist of the electron and hole from the different dots. And then again, by changing the barrier thickness, dot to dot distance, and you monitor the energy levels from the microphotoluminescence. And several years ago, Dresden group nicely reviewed a vertical quantum dot structure study, optical, and they based on tunneling regimes, the wave function overlap, and they observed anti-crossing by applying the external DC field. So they basically change the slope of potential. However, our approach is a bit different. We use laterally coupled quantum dot structure, and samples were grown by our collaborators. Those two people are experts in droplet epitaxy, and this is our sample. It's gallium arsenide, very clean, and capped by aluminum gallium arsenide, two droplets, and they are separated in the middle. And you just see the distance between two top is roughly 30 nanometer. So in this case, tunneling is very unlikely. However, we have to consider about dipole-dipole interaction. So in the case of dipole-dipole interaction, the alignment of two exciton dipoles are very important. For example, if you induced, if two dipoles are aligned along the coupling direction by using linearly polarized, we call H-polarized, which is parallel to the coupled direction, and the interaction becomes maximized. On the other hand, if the direction of parallel dipoles are perpendicular to the coupled direction by using V-polarized linear excitation, then the interaction becomes decreased a little bit. So our idea is very simple. Using the linearly polarized light, we want to control the alignment to dipoles and control the interaction between two quantum dots. But initially, we thought resonant excitation, it's more efficient. But surprisingly, we found even if non-resonant excitation is applied, for some reason, dipole alignments can be controlled through that non-resonant excitation. Exact mechanism is at the moment not clear, but we found there is some kind of interesting process between. Okay, initially we studied microphotoluminescence for increasing excitation power. As you see, under the non-resonant excitation with H polarized, after the interrelaxation, carriers are injected, but still dipole is affected by initial linear polarization. We think there might be some carrier distribution around the interface that induced kind of a local field, and a local field induced such alignment. And this is X exciton from the small quantum dot, therefore energy level is a bit high, and X2, bit large quantum dot, low energy. And you can also find a local biexciton corresponding to excitons X2, for example, X22, like that, and X11 from here. Binding energy is roughly 5 electron volt, nearly same too. And additionally, we found a coupled biexciton, which consists of the exciton from two different dots. It's called the coupled biexciton. Those two are local biexciton. On the other hand, if you apply the V-polarized excitation, you can find local biexciton, but there is no coupled biexciton. Additionally, there is no redshift. Here, there is a very significant redshift. And also, if you compare these two spectrums, those spectrums from the H-polarized one, here the energy level, spectral energy level is a bit higher compared to the case in H-polarized one. So energy is a bit high. That means wave function extent is a bit changed. Also, biexciton binding energy, local biexciton energy is also increased here. Yeah, wave function is changed. So we think, although it's a non-resonant excitation, the polarizations modified wave function extent through the local field, possibly. And also we analyzed photoluminescence intensity as a function of excitation power. And the blue one is from small quantum dot, high energy, and red one is exciton from large quantum dot x2, increasing exciton power, and luminescence increased. But blue one becomes saturated, but red ones shows superlinear increase. At the same time, coupled by exciton is also increased. So that suggests there is population transfer from blue, high energy, to low energy. And we also plot the redshift when the excitation is H-polarized along the coupled direction. On the other hand, with the V-polarized excitation, there is no such a thing. Luminescence intensity is always balanced, even if you increase excitation. And there is no spectral shift. Okay, to analyze it, we made a model based on dipole-dipole interaction. Again here, orientation, alignment is very important. And in dipole-dipole interaction, people defined dipole orientation factor. For example, here, this is 4, and this is 1. And the dipole interaction, more specifically, consists of 2 different terms. One is Foster resonant energy transfer, another one is the direct Coulomb. The magnitude has the same distance dependence, distance between 2 dipoles, but the mechanism is a bit different. This is about the transition dipole moment, and that is about the permanent dipole moment. In other words, occupancy. So, and occupancy also affects the polarization. So it's kind of a nonlinear effect. As occupancy is increased, wave function is modified, and oscillator strength is modified. Okay. Also, we studied the structure from the AFM. So given that height morphology, we roughly obtain potential, confinement potential value for electron and hole, and estimate an energy level, and consider in our theoretical model. And that is the simulation result based on such a H-polarized when 2 dipoles are aligned along the coupled direction. It shows redshift. So essential reason is flat interaction causes redshift, but the direct Coulomb causes blue shift. But here, when 2 dipoles are aligned along the coupled direction, flat plays more important role and causes redshift. And the magnitude of the redshift is very similar to our experimental result. On the other hand, with the V-polarized excitation, there is no redshift because 2 terms are similar, so they are cancelled with each other. So this is the summary of the structure. For example, X1, small quantum dot, bit high energy level compared to the X2. And you can imagine the local biexciton. Here again, local biexciton. And you can also think about the coupled biexciton, X1, 2, which consists of X1 and 2. And from the spectrum, we have identified X1 corresponds to that one, and X2, local biexcitons, and coupled biexcitons. But when you consider the transition of coupled biexciton to different exciton, X1 and X2, there should be 2 transitions, but I remarked only 1. So actually, 2 transitions are associated here, X2. We found, by chance, the transition 2 is overlapped with X2. Simply these 2 energy levels are exactly the same, so it's overlapped. That's why the magnitude of X2 is a bit high compared to X1. And in fact, this one corresponds to the transition 1. Okay, to confirm our idea, we performed the Magnetomicrophotoluminescence. So our idea is very simple. If 2 spectrums are overlapped here, the one is from the coupled biexciton with the different wave function extent. Here, X2 has a small wave function extent, then the diamagnetic shift will be different. So we expect the separation. But 8 Tesla is not enough, and spectral resolution is limited. So it was difficult to separate these 2, but we checked the line width. So X1 is small, but X2, which is overlapped with the transition 2, the line width is increased fast. So 2 emissions are overlapped. We also analyzed quadratic dependence of the diamagnetic effect. So the coefficient, that one is a diamagnetic coefficient, which is proportional to wave function extent. So free exciton and local biexcitons are similar, but coupled biexciton has a large wave function extent. So coefficient is large. Here is roughly 68. Others are 36 and 40. Yeah, so it is large. Wave function area is large. On the other hand, G factors are nearly the same for all those peaks. We also study time-resolved photoluminescence because wave extent is also associated with oscillator strength. So the larger the wavelengths, the larger the oscillator strength, and that gives faster decay time, if it's the case of radiative decay time. And when excitations are small, the difference is small, but as you increase the power, high energy X1 becomes fast, but X2 becomes a slow down. Okay, so wave function extends, becomes modified through the dipole interaction. So we plot the decay time versus excitation for two exciton. High energy decay times becomes fast, and the low energy is slow down. And coupled biexcitons is increased. Okay. On the other hand, with the V polarized excitation, there is no change. Okay. So H polarization is more efficient to control the dipole interaction. Again, we check the local biexcitons 1, 1, 2, 2, and compare with the coupled biexciton 1, 2. Here, by the way, from X1, 2, there is a energy transfer here. But from between the two local biexciton, there is no such thing. So those two, X11 and 22, simply decreased the decay time for increasing excitation time. Okay. And now we analyzed emissions polarization by using a linear analyzer. So the definition of an angle is like that. This is 90 degree for excitation. And for detection, this is a 0 and a 90 degree. Okay, so that's the result. Very anisotropic. So 90 degree, here 0. On the other hand, with 0 excitation, anisotropy is different. So although it's a non-resonant excitation, different anisotropy is obtained. That means the wave function shape will be different. Okay, for example, exciton 1 from here, under H or 90 degree excitation, we detect from 0 to 90, from 0 to 90 like that. So from this result, you can imagine about the shape of wave function. For example, here, 90, it's a large confinement size, so it's a low energy. Okay, here. And large oscillator strength, so intensity is a bit large. On the other hand, 0, the small size and confinement is large, so high energy, and intensity is small. However, in the case of 0 excitation, the shift is very small. So it's more circular, and it's more squeezed. And X2, those also shows a similar feature. Yeah. Large energy difference between 0 and 90 degree here with the 0 excitation, very small. And local biexciton, again, also shows a similar feature with 90 degree excitation. It shows red shift for increasing from 0 to 90 degree. With 0 excitation, very small change. Yeah, see the different energy. Confinement energy is different. And X2, local biexciton, also shows a similar feature. And this is coupled biexciton, and also shows a similar feature with the H polarized excitation. And we plot the energy difference from when the analyzed angle changed from 0 to 90 degrees. So it's analyzed angle. and energy difference from here 0, 20, 50, 90. So in the case of a zero excitation, then the spectral shift shows such way follows in linear type. And a 90-degree excitation, excitons and local biexciton shows large delta E. And this is for coupled biexciton with 90-degree excitation. Okay, so that's the energy difference delta E defined here. And time resolve again. So if wave extent or size is large in this scale, the oscillator strength is large, therefore the decay time will be very fast, or the decay rate will be very large. So 90-degree, for example, here, decay rate is large. Yeah, although it's time resolved PL, we assume it represents the radiative decay rate and increase in such a way for X1 and also X2 here. With a zero excitation, on the other hand, it shows a linear dependence, but if you compare with the case of a 90-degree, the magnitude is different. It's 2.3. Here is very large because oscillator strength along the 90-degree here is very large compared to that size. Again, the same feature. And biexciton X11, coupled biexciton 22 with 90-degree excitation. All shows similar feature. Okay. And with zero excitation X11, it's 2.9, but here see it's 3.5. It's large because this extent is large compared to this one. So H polarizable, 90-degree excitation, extend lateral direction of the wave function. Okay, so another interesting, surprising feature is selection rule. If you're familiar with quantum dot elliptical shape, we define the two principal axes, 0. And regarding the cascade transition from the biexciton exciton, you know, the angle is 0, 0, and a 90-degree, 90-degree. So you will get such a pair with the 90-degree selection and orange one. So this is cascade pair for the typical elliptical quantum dot. But in our case, it's different because our coupled quantum dot structure consists of two droplets, but two droplets are a little bit squeezed when the structure is formed. So the shape is something like that. It's not elliptical. So symmetry is further reduced. So it shows different selection rules. The 90 match to the 0, not 90. So 0 match to 90. So if you compare the exciton and biexciton emission pair, it's different. To confirm that, we perform HBT measurement. At first, from the exciton X1, selected at the analyzed angle 0, we observed anti-bunching. This is autocorrelation at 0 angle. And another angle 90-degree of analyzed angle, we confirm the anti-bunching. And the biexciton 90-degree anti-bunching. Here, anti-bunching. Now we move to the cross correlation between X1 and X2. That shows anti-bunching. That means these two levels are nearly two different sources. Okay, so it shows anti-bunching. And this is the most important part. We perform the cross correlation between these two transitions, 90 and 0. In the case of a typical elliptical quantum dot, it's not a pair. Okay, 90 should match to the 90 in elliptical quantum dot, but it's different. When 90 matches to 0, it shows asymmetric anti-bunching and bunching signal, because when the cascade emission occurs by exciton, this transition generate photon here, and this one generate orange photon, and that matched anti-bunching. However, bi-exciton's decay time is fast compared to the exciton one, so it caused anti-bunching. Okay. So they are cascade pair. On the other hand, if you do the cross correlation between these two, 90 and 90, it only shows anti-bunching. So these two are independent cells. Okay. And again, this is not local bi, it's coupled bi-exciton. Here, in the former case, it was a local bi-exciton, X11. Yeah. But it's coupled bi-exciton, consists of the exciton from two different dots. So coupled bi-excitons also shows cascade emission to the different excitons, X1 and X2. And if you do the cross correlation between 90 and 90, shows anti-bunching. And that one shows asymmetric anti-bunching and bunching signal, like that. Yeah, so indeed, it has a completely different selection rule compared to the elliptical quantum dot. Okay, so this is end of my story. So the key idea is here, when two droplets are formed to be a coupled quantum dot, there's a completely different selection rules. And there is not only the local bi-excitons, but also the coupled bi-excitons. Okay, thank you for attention.
Okay, thank you, Professor Kim. Very interesting talk. And now I think the paper is open for discussions. Someone wants to ask a question, or please write in the chat. If there's not yet any question, I can ask one myself, because I was very intrigued by the fact that the selection rules usually in the polarization are related to the block components, meaning to the atomistic part of the wave function. So then all these changes in the polarization are probably related with the whole part of the exciton.
Yeah, that's a good
point. Can you comment on this?
Yes, that's a good point. But here, our model, we only consider only heavy hole. We didn't consider the light hole. So hole plays maybe important roles. But at the moment, we tried to make a big calculation about this, but we have not completed. But at least experimental evidence shows cascade emission selection is different. But yeah, you're right.
Yes,
maybe
no, I mean, this result is amazing. Yeah. It's just that trying to understand, go a bit beyond that, or what were the reasons. And sorry, I missed a point. Is all experiments are done non-resonantly, I guess.
Yes.
Is that right? Okay. Yeah. So that somehow there is like a transfer of the polarization from the. It's very interesting. So if someone has a question, please write in the chat, or open your microphone if you can, and make the question. So I don't see much action.
Persistent current. Vladimir raised a question. Yes, it's a good point. Actually, in the recipe of the droplet structure, if they change the condition a little bit, coupled quantum dot becomes a quantum ring. So it's an intermediate stage. Yeah. If magnetic field is very strong, yeah, coupled quantum dot maybe cause persistent current, but it requires a very high magnetic field.
Okay, and there's no more questions. I I will ask one myself. Have you tested more dimers to see, for example, changes in the G factor, or if you have some statistics? I understand that this is very demanding to make all the experiments, but just in case.
Sorry, I didn't catch your question.
Yes, if you have explored more dimers.
Other material, you mean?
No, more. If you have performed more experiments on other quantum dot dimers to see changes in the, for example, the G factor.
No, we only focus on gallium arsenide. But I have experiment in some organic structures. It's not the quantum dimer.
I was meaning in gallium arsenide, but this is for one sample, I guess, not for one dimer. All the experiments.
Yes, yes.
If you have explored more to see the variability with the shape or size.
Yes, yes. We did experiment at different spectral range, but it also shows a similar feature. If you measure the microphotoluminescence, it has some broad line width, but within the spectral range, all shows a similar trend.
Okay. Okay, thank you very much. So the next speaker is Professor Alexander Golubov, who I'm afraid he could not attend the meeting today because he has a strong commitment with the university. So I think that what we can do is to make a pause and recover the session at 11, for example, in 15 minutes, so that we can gain some time for the next talks.
I started recording again.
Okay, then we will start with the contributed talks after the two invited talks we had previously. And the next speaker is Professor Nika, that we talk about the Phonon engineering thermal conductivity in graphene. So please share your screen, and it's all yours.
Yeah, thank you very much. Okay, just a moment.
Let's see if we are more lucky with.
Okay.
Now, perfect. We can see it.
Do you see my presentation?
Yes, yes, we can see it perfectly.
Yes, that's okay. Yeah. Okay. So I start. Good morning, dear colleagues. First of all, I would like to thank the organizing committee of the conference for the invitation to present my talk on Phonon engineered thermal conductivity in graphene. Together with unique electrical and optical properties, graphene demonstrates also an intriguing thermal properties. My name is Denis Nika. I am from Moldova State University, and I would like to start my, okay. So different parts of the presented work have been realized in collaboration between my theoretical group from Moldova State University, my team members Alexander Kashimazov, Artur Askerov, Kalina Isakova, and experimental research group of Professor Alexander Balandin from University of California, Riverside. I would like to start my talk from several words about my own country, about Republic of Moldova. So Republic of Moldova is a small European country this population about of 4 million people. You see in the slide a patch of European map. So in the east of Europe, between Romania and Ukraine, you see a small country, Republic of Moldova. The capital of Moldova is Chisinau. Moldova State University is the oldest university in our country and is situated in Chisinau. At the beginning of the current age, a new approach for improvement of kinetic properties of structures was proposed, phonon engineering or phononics. It is an approach to improve thermal or electrical properties of structures via tuning their phonon characteristics. So you can change electrical conductivity or thermal conductivity via modification of phonon modes. Why are the phonon properties so important for us? The answer is quite simple, because they determined the thermal conductivity, and also scattering of electrons on phonons limits electrical conductivity at moderate and high temperatures in semiconductors. And thermal conductivity itself is an important characteristic of material, because for the efficient thermoelectric conversion, we need materials with low thermal conductivity and high enough electrical conductivity. But for the fast evacuation of heat from hot points of modern electronic chips, we extremely need materials with high thermal conductivity. And graphene is a perfect candidate for this application. In my talk, I will briefly discuss phonon and thermal properties of graphene. I will show that graphene allows phonon engineering tuning of its thermal conduction. Thermal conductivity usually decrease as one goes from the bulk material to nanostructure. For example, the thermal conductivity of silicon nanowires or silicon thin film is by 2 orders of magnitude lower than in bulk silicon. Reasons for the thermal conductivity drop are decreasing of phonon group velocities, modification of phonon energy spectrum, and phonon boundary scattering. Since graphene is a monolayer sheet of bulk graphite, one can expect that graphene thermal conductivity should be substantially lower than that in graphite. Nevertheless, the first measurements of thermal conductivity in graphene, which has been done in 2008 in Professor Balandin's group from University of California, Riverside, demonstrate extremely high values of room temperature thermal conductivity of graphene between 3000 watt per meter Kelvin and 5000 watt per meter Kelvin. These values are by an order of magnitude larger than in bulk copper and by 2-3 times larger than in the best bulk heat conductor diamond or high quality graphite. Experimental results obtained in University of California, Riverside have required a theoretical interpretation. Well-known 3-dimensional models of heat conduction were unsuitable for graphene due to its 2-dimensional nature of phonons. Up to now, many accurate theoretical models were developed based on kinetic Boltzmann transport equation or based on classical or non-equilibrium molecular dynamic simulations. One of the first model explaining ultra-high values of thermal conductivity on graphene employed the valence force field model of lattice vibrations for description of phonon modes and the Boltzmann transport equation for calculation of thermal conductivity, taking into account all major phonon scattering processes in graphene: free phonon unclap scattering, point defect scattering, and H roughness scattering. Calculated dependencies of thermal conductivity on temperature are shown in the slide in the left panel for different concentration of point defects and different parameters of rough H scattering. In the right panel, you can see the dependence of thermal conductivity on specularity parameter shown for different flakes with different lateral sizes. We can conclude that thermal conductivity of graphene is very sensitive not only to temperature, which is typical for the most materials, but also to extrinsic parameters of structures, flake lateral sizes, and defects of crystal lattices. You can see that depending on these extrinsic parameters, we can change the thermal conductivity between 2,000 watt per meter Kelvin up to 8,000 watt per meter Kelvin. Experimental points are depicted here by circle, rhomb, and square. These points are from different experimental groups and were and were obtained using different experimental techniques. The influence of the crystal lattice defects on graphene thermal conduction is illustrated here. Black squares, red circles, and green triangles correspond to experimental values of thermal conductivity in graphene samples with defects induced controllably by beam irradiation. Curves show the theoretical results. Thermal conductivity drops fast with increasing the defect concentration from 2,000 watt per meter Kelvin up in graphene without defects, 200 watt per meter Kelvin in graphene with defects. Few layer graphene also demonstrate unusual dependence of thermal conductivity on number of graphene layers. In conventional semiconductor films, thermal conductivity usually increase when we increase the thickness of the film, because in this case we decrease the scattering, the boundary scattering of phonons. But in single layer graphene, in few layer graphene, thermal conductivity decreases with increasing the number of layers and approaches bulk graphite limit approximately for 8 monoatomic layers. Reduction of thermal conductivity with increasing thickness of graphene is explained by the opening up new channel for phonon scattering in few layer graphene. Theoretical results on thermal conductivity in rectangular graphene flakes with micrometer lateral sizes is presented in this slide. It is interesting to note that thermal conductivity demonstrates unusual non-monotonic dependence on the flake length. We explained this unusual non-monotonic dependence by the anisotropic free phonon scattering in rectangular graphene flakes and angle-dependent phonon boundary scattering. I would like to note here that thermal conductivity is strongly affected by the flake shape and edge scattering. For example, for flakes with large widths or for flakes with strong edge phonon scattering, we obtain the conventional dependence of thermal conductivity without non-monotony. In the case of square or circular graphene flakes, we also obtained monotonic dependence of thermal conductivity on the flake length. So non-monotonicity appeared only for rectangular graphene flakes. And in the last part of my talk, I would like to discuss thermal properties of twisted bilayer graphene. When two graphene layers are placed on top of each other, then can form a more potence. In this case, one layer is rotated relative to another layer by an arbitrary angle. There are two different Moire potents, commensurate and non-commensurate. In the case of commensurate potents, the periodic crystal structure retains, but the unit cell is larger than graphene unit cell, and each depends on the rotational angle. In the case of non-commensurate patterns, there is no periodicity in the crystal structure. Generally, commensurate patterns look like Flowers tracery. You can see here in the slide different commensurate patterns with different twisted angles: 21.8, 13.2 degrees. One important consequence of the rotation on Phonon states is increasing of the unit cell volume. Therefore, in the case of twisted graphene, number of atoms in the unit cell depends on the rotation angle and is larger than that in the single layer graphene. And as a result, there is difference between number of phonon branches in single layer graphene, twisted layer graphene without, single layer graphene, bilayer graphene without twist, and twisted graphene with different twisting angles. You can see that the number of phonon branches increases when one goes from panel A to panel D. This is direct manifestation of the twisting. And here in the slide, I show the dependence of thermal conductivity on temperature measured for single layer graphene, red and black points, for bilayer graphene without twist, blue points, and for twisted bilayer graphene, red points. The important conclusion is that the thermal conductivity in twisted bilayer graphene is smaller than those in the single layer graphene or bilayer graphene without twist for all considered temperatures. The decrease in thermal conductivity is related to change of phonon mode momentum due to twisting. Indeed, in this slide I compare 3 similar phonon modes in non-twisted bilayer and twisted bilayer graphene. These modes possess the same energies but different momenta. As a result, new channel for free phonon scattering appears in twisted bilayer graphene. You can see that decay of phonon indicated by blue ball into 2 phonons indicated by green balls is not allowed in bilayer graphene without twist due to momentum conservation law, and is allowed in twisted bilayer graphene. Therefore, free phonon scattering in twisted graphene is stronger than that in graphene without twist, with corresponding decrease in thermal conductivity. And the main conclusion of my talk you can see in the slide. So thermal conductivity of graphene is very high. In single layer graphene is very high and is in the range between 3000 and 5000 watt per meter Kelvin at room temperature. The thermal conductivity strongly depends not only on temperature but also on extrinsic parameters of flakes, on crystal on defects of crystal lattice, on edge roughness, on flake sizes, and therefore graphene gives us very interesting opportunities for tuning their thermal properties by changing extrinsic parameters. Thank you very much for your attention.
Okay, thank you very much, Professor Nika. And now the paper is open for discussion. Let's see if there are questions. Okay, Professor Fomin asked whether moire patterns in shifted bilayer graphene produce superconductivity at some magic angle. So do you see any magic angle for thermal properties of them?
Excuse me, repeat it once more, please.
Yes,
last
sorry.
Sentence.
Okay, the question. The first part is that there are superconductivity with at a magic angle in twisted graphene. I think the question is whether you see any thermal properties related with this magic angle.
Okay, so regarding the superconductivity, in the last years, were reported, several groups were reported results on superconductivity in twisted graphene with small twisting angle. But so my question, yes, but this is
no. The question is not on the superconductivity, it's whether the thermal properties might be affected by this magic angle. If you know of any relation between the magic angle for superconductivity with thermal properties.
Okay. So, okay, I understand. So the question was regarding influence between superconductivity and thermal conductivity for magic angle. I don't know because we did not perform these investigations. Okay. Probably the question is not simple.
No, of course not. In case you could comment on this. Okay, thank you very much for your talk. Very interesting. I don't see more questions, so we will. Sorry, there is a one question. Does the sound speed ultrasonic also depend on the number of layers if we can measure it?
Yes, there is a dependence of speed of ultrasonic on number of layers.
Okay. So if there are no more questions, we thank you for your excellent talk. We move to the next speaker.
Okay.
So okay, the next speaker is.
Thank you. Once more, thank you for your attention.
Okay, excellent. I speak on behalf of the audience. Okay, the next speaker is Gianpaolo Papari from the University of Naples, sorry, and the CNR spin, and he will talk about tuning the plasma frequency in terahertz grid metasurfaces for sensing applications. So,
thank you very much.
Are you here? Okay.
Hello. Yeah. Can you hear me?
Yes, perfectly. So.
Okay. Thanks for giving me this opportunity for this talk. I would like to thank all the organizers, and I hope the sharing. Okay. Okay. Can you see my slide?
Yes. Perfect. So you can start right now.
Thank you. So today I'm going to discuss about our last achievements of our group. We come from University of Naples in Italy, and our group is increasing, but what I'm going to show is mostly done by our small group composed just by me, Gian Corral, and Professor Andreone. So the outline is, I'm going to introduce the dependence on the plasma frequency of a metagrid according to the filling factor of a unit cell. I'm going to explain this concept. Then we are going to use this property to design specific metasurfaces to apply sensing according to some specific change in the features of transmission properties of a metagrid. And we are going to then introduce also a way to improve the quality factor of the resonances of these metasurfaces. And I will propose then a couple of fabrication processes that uses laser ablation, femtosecond laser ablation, to produce new metasurfaces, and then I will go to the conclusions. Just a few notes on time domain spectroscopy. We are working in terahertz regime. Then later I will going to introduce our setup. And basic information is given by the way the transmission can provide us information on electromagnetic parameters, especially refractive index or the electric function of a material. Here on the left, we can see an impinging signal up an homogeneous slab of thickness D. At each interface, air substrate, sample, the signal divides in two. One part is back reflected and one part is transmitted. The transmitted part again on this other interface is going to undergo another division into a back reflected and a transmitted signal, AT1. The back and forth mechanism of the internal reflection has a clear fingerprint into the time domain signal. Here, you can see my arrow, my pointer. Can you see?
We can see it perfectly.
Ah, okay, thank you.
Please.
So the black one, the black signal is the reference one, that is the intrinsic signal generated by the system in absence of the sample. When we put the sample, we can see the red signal that is composed by the main transmitted signal that is delayed and damped according to the complex refractive index of the sample. And then the number of these multiple reflections can be seen according to 82, 83, 84, and so on. Make spectroscopy of this sample means to pass to the frequency domain. So we apply the Fourier transform of the signal passing through the sample divided by the Fourier transform, fast Fourier transform in this case, of the reference signal. This is a classical model where we can, according to the Fresnel coefficients and the phase accumulated by the signal after the thickness D, as these simple expressions. And of course, the periodicity of the reflected signal provides a Fabry-Perot terms that in transmission is, featured by a clear harmonics that is related to the refractive index and the thickness of the sample. What I want to say in these slides is that basically we have a way to simply achieve information on the refractive index and the electric function of the sample. I have to say that this relation that relates refractive index and to the electric function works only with non-magnetic materials, which are, the samples we are analyzing in this case. It's very important, the electric function, because to our aims, because the real part of the electric function gives information on the phase of the material. When it's positive, we are dealing with something that is going to become insulator. When it's negative, is a plasmonic media with a metallic features. Here we're going to introduce briefly our systems. We have more systems. In this case, this is a Menlo one fiber-coupled photoconducting antennas. And we have a transmitter, we have a receiver, and we also have, in this case, the complete optical line with collimated lenses and focalization lenses. I have to say that in this experiment, we are working just with collimated lens. We remove the focus lens because we want a signal that is good approximated by a plane wave. This is made in order to combine also results with simulations which are performed with the commercial software CST microwave systems. The two grids we are using to make sensing are just made by a foil of FR4. It's a commercial insulator made for circuits and PCBs, 160 micron thick, this green part. And there is a metallic grid, in this case in two shapes of just grid, we have called it grid metasurface, or in shape of chessboard, CB metasurface, which are characterized by two different filling factors. What is a filling factor? The filling factor is the amount of metal filling a unit cell. In the case of a grid 1, we have that 3/4 of a unit cell is filled. In case of chessboard, roughly 1/2. This information is going to use later on. Now I would like to give the transmission features of these two metagrids, where we can see a series of peaks which are in a good metamaterial regime, I would say, where, of course, the wavelength is a couple of times larger than periodicity. In this case, periodicity is 600 microns. So we have these two features. What we are interested now is that these features, these metasurfaces have been investigated in this paper. And we have reconstructed all these sort of modes, or if we like, excited states of the metagrids, which can be modeled through high-order surface plasmon polaritons, which are featured by specific momentum, and the frequency is much similar to the threshold frequency of a waveguide, but in terms, there is no, of course, relation with the geometry of a waveguide. There is a relation with the periodicity of unit cell. And each resonance is labeled by two indexes according to the X and Y nodes of the wavelength. So we are in the plasmonic regime, and we have these features. We want to use these features, this transmission feature, to make sensing. Last information, of course, before skipping to the sensing, is that here we have analyzed in the scientific report the dependence of the plasma frequency of these two metasurfaces according to the filling factor. I just want to provide this hint because it's more important, because if we want to calibrate, tune metasurfaces according to the position we want to see these peaks, which are related to the enhancement of transmission provided by the excitation of high-order plasmonic excitations, we can see here, studying the electric function of the entire metasurfaces, that the crossing between the negative and positive part of the real part of the electric function of the two metasurfaces happens around 200 gigahertz. So we want to see if we have studied through simulations the change of these transition frequency, that basically is the plasma frequency of metasurfaces, according to the filling factor. Below this frequency, the band below this frequency is such a way that behavior of the metasurfaces is completely homogeneous. You don't see any peaks. It's like a mirror. The transmission is almost zero. And no features is characterizing the spectrum. Above this peak, we see the onset of high order plasmonic excitations since the average dynamic of the metasurfaces, the electric function is positive, and the wavelength starts to be comparable. I mean, the wavelengths inside at the interface. So the wavelength at the interface metallic insulator is scaled by the dielectric constant of the substrate. We see the onset of this peak. The dielectric constant of the metasurfaces is positive. So we have labeled this behavior above the transition frequency like a photonic crystal. Basically, this behavior, we have proved that the main arrangement made by Pendry in his papers can be scaled also to a bidimensional structure. Pendry has developed his papers mostly with the 3D grids. We have tried to adapt this scaling to a 2D metasurfaces, and it works quite fine. Now, we have peaks. We want to use the metagrid to sense the dielectric properties of an unknown analyte. What we can do? We can take these metagrids, we can pour an analyte, and we can cover the structure, in this case with the glass, because I have a layer of glass 160 or 150 micron in thickness that we have characterized in order to improve also the reliability of simulations. I have to say that the analyte in this case is studied just changing its real part. The imaginary part of the analyte is kept to 0 just because this is a beginning work. What we observe when we have realized this kind of structure is that the transmission peaks undergo a shift according to the electric constant of the analyte. Therefore, if we can monitor and study the change of the position of these peaks according to the electric constant of the analyte, we can make a sort of we can make a label-free sensing. So just having in our database the way these peaks shift according to epsilon x, we can provide a sampled, because we studied just the peaks, so just a few points to characterize the dielectric constant that becomes a dielectric function, because we have a few points over a band of about 1 terahertz, half terahertz in the case. And so sampling, we have a fast way to characterize an unknown analyte, just creating a database on the shift of these peaks. The problem is that when we, in order to create this structure that is very good, because now we have specific information on the volume in the unit cell of the analyte, we can also proceed then to make some sort of retrieval processing in order to extract from the transmission of this very complicated structure just information on the dielectric constant. So aiming to providing the right constraint to apply properly models to this system, we have lost signal to noise ratio. It's decreased because the higher is the number of layers, the higher are losses. And so the information degrades. And this is clear in this slide. In this figure, log the transmission, we have studied the way the transmission, the modulus of transmission changes according to the dielectric constant of the analyte. As we can see, these peaks in this contour plot are now quite wide, and a way to follow the change, the movement of these peaks, is quite hard in this case. Therefore, we have developed a code, a simple code, that goes to study the derivative of the area underneath the transmission peaks. This curve here, the citation was before, it's on a sensor, this algorithm basically provides an enhancement of the quality factor of each resonance that follows, in any case, the maximum, so it's reliable as process. And now we engineer the quality factor of this resonance, and we can push down the width of each resonance down to a few points in frequency domain, so extremely high. Now, applying this process, we can see here the log of Q, and we have a very clear dynamics of the frequency of the transmission peaks, so we can trace them out. And here we have labeled basically the frequency point in terms of the wavelength, lambda in microns, and we have expressed the dielectric constant of the analyte in terms of its refractive index. Now we have clear curves. We can apply the derivative in order to extract the sensitivity. These sensitivity now are among the highest values available in literature. Of course, now we can model the transmission. We have much more information to model the transmission of metagrids in order to have a group of resonance in the band where our signal to noise ratio is the highest possible. But we want also a procedure to realize these metasurfaces fastly, because we now have a great experience with simulator, which are very reliable. So if we provide a simulation, we are sure that the real metasurfaces will respond in the same way. Here we propose a couple of techniques. I mean, it's based always on femtosecond laser ablation, are structures made in collaboration with the group of Professor Amoruso. And with the femtosecond laser ablation, we have realized several metasurfaces and also complementary ones. Here we can see a few examples in the scale, of course, of tenths of microns, which are in the right periodicity for our goals. And the samples, of course, we start with a substrate of silicon with on top 200 nanometers of gold, and then we ablate partially, of course. And this is basically the main achievement, where we have overlapped to our experimental achievements, in this case just the transmission modulus, the simulations results. We can see here in the first very simple metagrid just made of periodic holes, we have achieved maybe the highest quality factor in resonance in the terahertz regime, that is almost 90, and also dichroic, in this case, dichroic metasurfaces, where we can tune the enhancement transmission just according to the polarization of impinging wavelengths. On the right, we see 4 examples of dichroic metasurfaces made of tiny resonators in different shape. It's very interesting in these 2 slides. Of course, the change of polarization provides a really gap change into the transmission, and this is very good for several technological applications and sensing as well. Always with the femtosecond laser high energy energetic pulses, we can extract from we can fabricate metasurfaces inducing a change into the phase of a diamond. We can turn it into graphite. What we have here, this is made in collaboration with the C group CNR, so Alessandro Bellucci, Daniele Trucchi, and Antonio Sant'Agata. We have written now this paper on carbon, but this is just the beginning. These are our preliminary results. And here there is 2 very nice images. On the left, graphitized layer is what we have in terms of graphitized layer itself. because the continuous repetition of pulses in order to induce the onset, the transformation of diamonds, at a certain point creates surface plasmons whose interference create these ripples. As you can see, where is my arrow? These ripples, which are long a few hundred nanometers and in periodicity roughly 50 nanometers. We have also studied the structure that is obtained by removing this graphitized layer. When we remove this graphite from the top, we have here what we have called the black diamond, because the sample is always black, but of course for optical reasons. We can see that underneath these ripples, I mean, these ripples are made now just of diamonds and are on nanoscale. But even in the terahertz scale, we can measure the change due to the dichroic properties now provided by these ripples. And here we have the main results on this graphitized layer. We have performed two different measurements. One when the electric field is parallel to these ripples, and the other one when it's perpendicular. Usually they call TM and TE polarization. And what we can see is that it's very nice. The black curve is the curve obtained just passing through the diamond, not processed. Indeed, we can see, I mean, Fabry-Perot Echelon effect. The red curve is the electric field, a terahertz signal passing through the sample, the graphitized one. This is for the graphitized layer. What is interesting here is that the first, where is my arrows? The first reflection in TM, so look the red curve, is following the same phase of the impinging signal. Instead, in TE is as a pi shift. This change into the reflection is a clear fingerprint that when the polarization is TE, so when the electric field follows the directions of these wires, graphitized wires, we are measuring something that is almost metallic. A metallic layer provides a pi shift into the first reflection because epsilon is negative. Instead, when it's TM, it's like an insulator once. Okay, we have summarized this information studying the modulus of transmissions. The dots represent the TM polarization, so when the field is perpendicular to wires, and TE when it's parallel to wires. Of course, the black ones represents the bare substrate and there is no change. The blue one represents the black diamonds, that is the sample where the graphite has been removed, but the ripples still provide a change into, provides the dichroism at the sample. And the orange curve is what we have when we measure the two polarization of a sample graphitized. And it is quite interesting. It's comparable with some other results in literature. And now we are working to increase, of course, this change in order to realize optical devices. In conclusion, we have developed time domain spectroscopy for label-free sensing. We have studied the change of plasma frequency of metasurface that we have called the transition frequency according to the filling factor of the unit cell in order to design specific metasurfaces for several uses, in this case for sensing. We have developed a code to enhance the information provided by the transmission of a sample with several losses. And we have also characterized a few metasurfaces which have been fabricated with the femtosecond laser pulses. Thanks for your attention.
Okay, thank you, Gianpaolo. It was a very long talk. I mean, I think it's 5 minutes above what was expected, but it was very clear and very interesting. I didn't want to interrupt because we have some time saved from the previous talk. But I think Vladimir has a question, and I think he can ask himself. Please, Professor Vladimir, can you unmute your microphone?
Hello, Gianpaolo.
Hello,
Nice talk. My question concerns the properties of your meta grids as metamaterials with specific topological properties. Have you observed, or is it feasible to observe experimentally the interactions of signals around different structural units of your meta grids, whether it's whole or peaks in ripples in black diamond? So what about interactions?
Well, actually, we have to say that concerning specifically the carbon black, so the diamond with these ripples, we are still performing studies. What we can say is that, of course, there is in terms of topology, in order to make the study, we should also try to get several different features underneath. So we would like to somehow produce these structures also using different laser shapes, so that we can also have some different, not only just straight ripples, but also other different shape. In this case, we can see if we have also in phase of the signal some properties due to the change of the design, let me say. For now, I can just say that basically this is due to a concept of scattering, local scattering, and no much more. Thank you.
Thank you.
Okay, thank you, Vladimir, also Gianpaolo. Can you stop sharing the screen?
Of course,
because we have to move to the next speaker. I'm sorry, we have no more time.
I don't know
recovered
how to stop.
I think in the top part of your window, you should see something, or I can stop it for you. No problem. Perfect. Thank you again for your nice talk. So the next speaker is Yao Xiong, who is making an extra effort because it's in the US. So for him, it's it's still at night.
It's very early.
He comes from Clemson University. Are you here? Can you hear us?
Yeah. How about
okay,
you?
So
can you hear me?
Please share your screen and.
Okay. So can you hear me?
Yes, we can hear you perfectly.
Okay, that's great. Okay, so first, thank you for giving me the opportunity to present our recent work. And I'm going to share my screen. Can you see it?
Yes, we can see it perfectly.
Okay.
Thank you.
I'm going to start.
Oh, okay, it's 15 minutes, so let's start.
Okay, that's great. Thank you.
Hello, my name is Yao Xiong. My topic is dynamic control of pattern formation and restructuring in constrained hydrogel membranes. Our research is motivated by that the functionalities of materials, such as adhesion and wettability, can be controlled by patterns. Patterns in gels are a result of instability, which can be triggered by applying confinements or utilizing the mismatch in strain and stress. Here, I show one example of hydrogel-based metamaterials, which shows a negative swelling ratio during water absorption. This material is composed of polymer, hydrogel, and elastomer. Due to the swelling of hydrogel, these initially straight beams are bent, leading to the reduce of the structure size. It also shows a tunable stress-strain curve by controlling the time of hydration. Our research goal is to dynamically control the pattern formation in confined hydrogels. Here I show some examples of swelling-induced patterns where hydrogels are confined by attaching the surface to a skin or by clamping the edge of the membrane. For thermal-responsive hydrogels, varying the temperature could result in the change in their volumes. If no restriction, those hydrogels can freely swell or shrink in all three directions, and we cannot achieve patterns. However, if one or two edges are clamped and the expansion is sufficient, we can observe buckling in those confined hydrogels. And in our research, we choose this type of confinement. The process of gels undergoing changes in their volumes in response to external stimuli is called a volume phase transition. In our research, we use polynapalm hydrogel, which has a lower critical solution temperature around 33 degrees Celsius. We investigated the pattern formation in confined polynapalm hydrogel by simulations on continuum scales. Our computational approach is 3D gel lattice spring modeling. In this approach, gels are discretized into elements. Upon equilibrium after isotropic swelling or shrinking, we can solve this equation to get the equilibrium volume fraction of polymer in each element, where here the chi is the polymer solvent interaction parameter. C0 here is the dimensionless cross-link density, and the phi0 here is the volume fraction of polymer at preparation. Once getting the value of phi equal, we can use the degree of swelling to estimate the relative change in the gel due to volume phase transition. Taking the interaction parameters of polynapalm hydrogel and the other parameters from the experimental study here, our simulation approach has been validated to reproduce the volume phase transition in polynapalm hydrogels. In this plot, each square represents one independent simulation run. In case 1, gels has relatively higher C0 and higher phi0. Increasing the temperature, those gels shrink and show a continuous volume phase transition. And the gels in red, which have a relatively lower cross-link density and phi0, they undergoing discontinuous volume phase transition. Here are the sightings and the scales in our simulation. Gels initially are flat and equilibrated at a relatively higher temperature. After fixing the two edges, we quench down the temperature of hydrogel to a relatively lower value. We characterize patterns by the amplitude and the wavelength. Later, I will show the onset of pattern formation in confined hydrogel can be identified by the relatively swelling ratio alpha, which can be analytically calculated by the equation from previous slides. I will also show the dynamic control of pattern formation and the hysteresis loop observed in confined gels. In our first scenario, the temperatures of confined gels are quenched down to various values. Here is one example of the development of pattern formation. In this image, we plotted the wavelength and the amplitude of fully developed patterns from our simulations. Each point represents one independent simulation run. We tried two initial temperatures and find samples with same initial size and cross-link density would have similar patterns at a given alpha. And we can observe buckling if the alpha is larger than the critical value alpha c here. We also find that beyond the critical point, increasing the alpha results in the decrease of wavelength and the increase of amplitude. And the amplitude has a relationship between the alpha c and the alpha. Based on the linear elasticity, This part is related to the compression applied on gels by boundaries. A similar dependence of amplitude on the compression was also found in elastic plate. In order to understand the fully developed patterns in confined hydrogels, we performed a linear stability analysis using 4.1 common equations, which have two components. Here, dE is the bending stiffness of hydrogel plate, and E here is Young's modulus, and V is the potential ratio of hydrogel, which can be achieved by GLSM simulations. Zeta is out of plane displacement, which describes the surface topology. Due to the balance between the thermal stress and the compression, the gel plate is assumed to be equal but actually compressed. So we can relate the strain to the alpha. Solving the 4.1 common equation, we can get the predictions in both the minimum compression for pattern formation in confined gels and the corresponding wave vectors. Here, we summarize the wavelengths of barcode samples from 5 series of simulations, and the data corresponding to samples in previous slide are marked by the box. The samples at the critical points in each series are in light blue. We found the wavelengths of those samples shows a very good agreement with the analytical prediction. In the previous study, where gels are clamped at one edge, they found the wavelength also linearly depends on the sample's width. Above the critical point, the wavelength of buckling becomes smaller than the analytical result. We now focus on the dynamic control of patterns by introducing cooling heating cycles. The blue line here is the temperature profile. The temperature of the sample is dynamically changed between 30 and 22 degrees Celsius. The red line here is the amplitude, and if the amplitude is above the green line, it means that the gel is buckled. During cooling, the sample remains flat until the temperature is below the critical value here, and the gel can promote the buckling to a higher critical temperature during heating. So the temperature can be separated into 3 regions. No buckling observed in red region during both the cooling and the heating process. In the gray region, the sample shows buckling only during heating process. And in the green region, we observe buckling during both the cooling and heating processes. By introducing cooling heating cycles, we also observe the hysteresis loop in the wavelengths, comparing with stationary case where the confined hydrogel can fully develop the patterns at different constant temperatures. We find the dynamically controlled sample has a smaller wavelength, and the wavelength remains approximately constant during the cycles. We also find that increasing the rate results in that the critical temperature during cooling would be shifted to a lower value, and the critical temperature during heating would be higher. In other words, we could control the size of hysteresis loop by changing the rate. Here, we periodically stretch and compressing the gel along the width at 24 degrees Celsius. The blue line here is the strain profile, and the red line is the amplitude. Before introducing cycles, we quench down the temperature of the gel from 30 to 24, and the confined gel takes enough time to achieve the fully developed pattern. If the amplitude is above the green line here, it means that the gel is buckled. During stretching, the sample remains buckled until the strain reaches at a critical value, and the gel maintains the flat configuration to a lower critical strain during compressing. As a result, the strain can be separated into 3 regions. In the red region, no buckling observed during either stretching or compressing. In the gray region, only the stretched sample shows buckling, and in the green region, we observe buckling during both processes. By using stretching compressing cycles, we also observe the hysteresis loop in the wavelengths. Comparing with stationary case where patterns are fully developed in gels with constant width, we found the wavelength of the dynamically controlled sample can remain approximately constant. A faster rate shifts both critical strengths during stretching and compressing to higher values. Here's the summary. We show the control of pattern formation in confined thermoresponsive hydrogel by using either cooling heating cycles or stretching compressing cycles. We also showed the dynamical control of surface topology and the hysteresis loops observed in both the amplitude and the wavelength. Our research is supported by the NSF F-score program. Thank you for your attention. I'm open to questions.
Okay, thank you very much.
I don't know why my sharing is stopped. So should I stop it, share it again?
As you wish. I mean, depending on the questions, I think Vladimir wants to ask something. No? Ah, okay, sorry. I saw a hand and I thought you were raising your hand. Okay, and what type of applications are you targeting for these hydrogels?
You mean the first publication or our target general?
Applications. Where do you?
Oh, sorry, applications.
Plan to? I mean, for sensing or for doing some devices.
So in our group, we are focusing on the simulation. So we do not have a specific or particular application. So we just want to find the relationship between those topology with the properties of hydrogels. So what we found can be applied to any other types of hydrogels. So this is our main goal.
Okay. Is there any other question in the audience? Let me see. Wait. If not, then we thank you, the speaker again. Thank you again for your extra effort in being alive with us.
Thank you.
And
so I can stop sharing.
Yes, please. Excellent. So then we move to the last part of the program for this morning session, which is sorry, I missed that. Which is the flash talks on the pre-recorded talks and posters. So, Oliver, do you want to start?
Yes,
with your flash talks? Okay, in case you haven't noticed, in the program there is a link to a YouTube channel, well, to the conference YouTube channel, where there is a playlist with 4 talks that we couldn't allocate in this today program, and you can see the talks in full length. So here is just a flash talk, a brief summary on those topics, and we can discuss about them later. Okay, Oliver, sorry. Please,
okay.
You can start if you want.
Yeah, thank you very much for the introduction. So I will present on a joint work together with my colleague Karin Gambarian from Yerevan State University on the nucleation chronology and electronic properties of indium arsenide antimonide phosphide graded composition quantum dots. as Jose already announced, that's the flash talk, so more details can be found in the pre-recorded talk. So generally, why are we interested in the material at all? So indium arsenide antimonide phosphide allows a well-defined access to the mid-infrared spectrum, with applications being in thermal detecting, gas sensing, photoresistors, energy harvesting, photoconductive cells, and so on. And the systems we are talking about today have been grown by liquid phase epitaxy. That's a, I must admit, a kind of old-fashioned but very robust and inexpensive approach to produce semiconductor heterostructures. And it has a specific advantage, namely you can easily incorporate compositional gradient within a nanostructure. So you can on purpose produce a composition gradient to reduce strain and so on, in particular in materials with a large lattice mismatch. And moreover, my colleague Karin achieved very stable
excuse me, Oliver.
Yes.
We are only watching the ocular application first. Is that, I mean, are you browsing the slides or?
Yes, I am browsing the slides. Let me see.
Okay, it's not working.
Stop share because I saw it. It actually showed the right thing, but it seems not to. Is this better now? You see the motivation slide?
Now, yes. Can you change slide so that?
Yep.
Yes, now it's working.
Okay. So yeah, where did I stop?
Sorry,
so my colleague Karen managed to. No. Please. I didn't see anything what's went wrong here. So Karen achieved to produce these nanostructures in a reproducible manner, so that they are essentially useful for future applications in the infrared spectrum. So these are pretty much the structures that Karen was able to grow for us. So we have characterized them via atomic force microscopy and scanning tunneling electron microscopy. We have quite some idea on the size of these systems. So that's about a diameter of 75 nanometers, plus minus quite a bit, and the height of 8 nanometers, which seems to be pretty stable. We could estimate the surface density to be 3 to 7 times 10 to the 9 per square centimeter. And we would expect as I said, a composition gradient, as you can see down here, with a maximum antimonide content of 20% at the top of the systems, and the maximum of the phosphide content here at the bottom of about 15%. We characterize the samples using Fourier transform infrared spectroscopy at almost room temperature. So we have seen the absorption of the graded composition quantum dots at around 3.83 microns. For comparison, the indium arsenide is about 3.47 microns. And we could also see that the surface properties are modified quite a bit by these systems, surface resistance, and you see this peak here in the bulk substrate, which is not there anymore once we have these graded composition quantum dots. So we have then started to do some simulations. We have employed continuum elasticity theory and an 8-band K.P model for zinc blende crystals. All that was implemented within a plane wave framework of the Swing software library. Let me note that the system we are talking about is a type 2 heterostructure, so the holes should be confined in the quantum dot, the electrons in the substrate. So we had a look here only at the hole states because these are then the ones of interest. All parameters for our simulations were taken from Wohlgaftmann's paper from 2001, and we have then applied Varshny's correction that we correct our energy values to the temperature of the measurements. So that's the elastic properties. What you see down here is the hydrostatic and the biaxial strain distributions. So magnitudes are about a bit more than 1%, plus and minus here. And not too surprising, the extrema occur here mostly at the tip. It's not too surprising because, first of all, well, it's a tip, so this is where elastic relaxation happens first. And second, it's the maximum antimonide content up there, so of course that's another reason. And what we also see is that what the strain does, if you have a look here at the band plots, the conduction and valence band structure along the central axis of this quantum dot, you see that the conduction band due to strain, that's the solid line here, is modified to something like a flat band, whereas unstrained it would be here this dashed line. Valence bands are not affected too much. And what we see is then the whole states localizing somewhere here in the top of the system. I'll have a closer look at that. So that's the electronic properties. We have looked at transition energy as a function of the graded composition quantum dot base radius and the respective height. So the base radii can be seen here in these numbers on the corresponding lines, and the heights are down here. And then, and what you see here in the inset is basically how a whole state, that's the blue thing here, looks in such a graded composition quantum dot for one of the typical systems. And we have then taken a sample of our simulations, which is this gray frame down here, which pretty much matches the values we know from experiment in terms of diameter and height distribution. And then we have mapped the respective energies from our simulations after Varshny correction and so on to this particular range. And this is pretty much the intensity peak we could see then. It has its top at 3.829 microns, which matches the experiment extremely well. So the experiment, I remind you, has 3.83 microns. So we believe we have found here something to provide a well-suited approach for theory-guided design for such systems. So thank you very much. And for more details, please have a look at the pre-recorded presentation and feel free to ask questions in chat or however. Thank you very much.
Okay, thank you, Oliver. Very on the spot talk. I think we can open the microphone to Vladimir so that he can ask directly.
Yes, I'm trying to open. Did I open it? Yes.
Yes.
So Oliver, because it's very promising, I would like to know already now which composition precision is needed in order to make Yo and Karen's quantum dots and quantum rings available for the existing market demands in the field of micro-optoelectronics.
Yes.
From theoretical point of view, everything is clear, but how close are they to practice?
Yes, yes. So what you basically see is they have a certain density of or a certain distribution of diameters and so on, and the same will certainly apply also to the antimonide contents and so on. So to the composition of the materials. So of course, from theory side, this is very simple. So I could just look for one specific wavelength we are interested in, but inevitably we will have a peak, which is not which will be widened at some point. What I can tell you, however, is that Karen is already producing devices that they use for gas sensing. So we can, with our simulations, we can point to a certain range, and it seems that the quality of the systems is in fact able to put this into application already now. So of course it depends on how accurate you want to define your wavelength, but I think that's the common problem for all quantum dots. So it seems possible from the growth point of view.
Okay, thank you.
Thank you. Also, Professor Kim has a question.
Yes, yes, I have seen your. Yeah, sorry.
Yes, my question is, I wonder whether there is any localized state. For example, if you compare with the theoretical calculation energy to the experimental photoluminescence, did you measure the wide luminescence width or any energy difference between luminescence and theoretical energy?
Well, we have seen the spectrum that experimentalists measured, and that does not match the bulk indium arsenide. So there must be something localized in these systems. As far as I know, the lifetimes are quite large, which is not too surprising either, because we have a type 2 system, and for sensing, essentially what you want is large lifetimes. So there must be something localized in there, and our simulations clearly show at least the ground state is localized. And given the size of the system, I would also expect, we haven't looked for excited states, but I would expect there's certainly a handful of whole states that's also localized there. Of course, no electrons, because they should be in the substrate.
Okay, thank you.
Okay, thank you, Oliver. I think we can move to the next flash talk.
Thank you.
And the next talk is done by Igor Bogush from the Moscow State University on modeling phonons. So please.
Do you see my screen?
Yes, it's working.
Okay, good afternoon, dear participants of the conference. First of all, I'd like to thank organizers for this opportunity and would like to talk today about modeling of phonons in rolled up nanostructures. This work was done by me, Igor Bogush, and Vladimir Fomin. We are studying rolled up nanostructures. They are thin silicon membranes covered by oxide film, and they can have a different number of windings. And experimentally, it was found that the larger the number of windings, the lower thermal conductivity is. For example, for one winding, we have circa 9 watts per Kelvin meter, and for 5 windings, we have around 3.5 watts per Kelvin meter. For such rolled up geometry, we can simulate such rolled up geometry with Archimedean spiral, and we used the tool of general relativity, the differential geometry, to use this geometry. However, we found that it's not a problem to find that if the width of the winding is small enough with respect to the average radius of the spiral, then we can neglect geometrical effects, but we have to preserve the information about contacts between windings. After we neglect geometrical effects, the cross section can be represented as a flat structure with special boundary conditions. For example, here's the structure. Blue lines represent free boundaries, and red arrows are contacting boundaries. And we have to identify these red arrows with each other, preserving their direction. As the problem as the structure is large enough for calculations, we would like to reduce our problem to one-dimensional problem. To do that, we identify side boundaries and outermost and the innermost boundaries of our structure. One can show that such identifications introduces only small errors, and this error is especially small if the number of windings is large enough, for example, at least 4 or 5 windings. Such structure is called flat torus in topology and differential geometry. Okay, another approach to simulate this topology is a planar approach. We can approximate our structure with a planar structure, and the cylindrical approach when we can approximate our structure with a set of concentric cylinders. And again, if we neglect infinitesimal small geometrical effects, these two approaches gives they give absolutely the same result up to the discretization of the moment along with winding number. Here's an example of the spectrum and group velocity that we got for the nanostructure with radius equal to 1 micrometer and 2 windings. If the width of the winding equal to 20 nanometers, here we used cylindrical approximation, and phi is a transversal mode, and chi is a mixed longitudinal transversal modes, comparing many different results with different approximations and winding numbers. We found that the global structure of the spectrum doesn't depend on winding number. The spectrum lines are expectedly denser for larger number of windings, and very interesting that different topological approaches come to the foreground only where the confinement effects begin to play an important role. In the 15-minute pre-recorded video, you will find more information about thermodynamic properties for such structures. And briefly summarizing, I would like to say that different approaches allows us to estimate and to calculate topological effects on thermodynamic properties. Thank you for your attention.
Okay, Igor, thank you very much for the introduction to your full-length talk. Is there any question in the audience? Let's check the chat. Well, it seems that there are no questions. So then we can move to the next speaker.
Thank you again.
So thank you for your talk. To Isakova, please. Can you hear us?
Yes, yes.
Okay, excellent.
I will share
Okay, Isakova comes from the Moldova State University.
Hello, my name is Kalina Isakova, and I represent one of the laboratory of. I'm working in laboratory of nano.
Excuse me, can you put in the in presenting mode?
You don't see my presentation, or?
No, we see your application. We see the PowerPoint, not the slide projected. Now it's perfect.
Okay.
Yes, now it's okay. Sorry.
Okay. I'm working in Yepa Kotilov Laboratory of Physics and Engineering of Nanomaterials with Dr. Denis Nika, and you already listened his report on phonon engineering and about increasing the thermal conductivity. Another side of phonon engineering is reducing thermal conductivity in order to obtain thermoelectrical materials. The thermoelectrical properties of bulk materials and their nano-dimension analogs can be quite different. Even in simple nano layer, in simple nano layers, nano wires, the silicon has lower thermal conductivity than in bulk. In order to obtain more lower values of thermal conductivity, the different researchers tried different technologies, different materials, different geometrical parameters. In our work, we studied theoretically the microtubes, or maybe they can be called as nanowires, which consist of layers of silicon and silicon dioxide, which are alternating. In our theoretical investigation, we represented these experimentally obtained structures as nanowire with the cavity inside and different number of shells of silicon and silicon dioxide. This is the schematic view of theoretically studied nanostructure. For our investigation, we used the lattice dynamic model for in order to obtain phonon dispersions, face-centered cubic model. The dispersions in such structures differs from the dispersion in nanowire. They are more flat and they are concentrated in a lower energy range. So the velocity of phonon modes is lower than in in simple silicon nanowire, and the flux of the thermal thermal flux will be propagating with low velocity, and the thermal conductivity, we already can say that thermal conductivity will be lower than in simple nanowire. The decrease for there is the decrease for different number of with the decrease of phonon group velocity for greater number of shells. For calculation of phonon thermal conductivity, we use Boltzmann transfer equation and three types of scattering mechanism. We calculated in different ways. One way we grouped unclocked scattering, impurity scattering, and boundary scattering, and the other our calculation was carried out for unclop impurity and effective scattering in amorphous silicon dioxide. Conform our calculations, the greater impact in scattering have boundary than amorphous silicon scattering. We obtained the reduction similar to the reduction which are obtained for experimental, which are obtained in experimental results. So with the increase with number of shells, we decrease the decreasing of thermal conductivity is 2 times and more. And the conclusion. Modifications of phonon dispersions. There is modification of phonon dispersion in silicon dioxide nanotubes, and the dose maximum shifts to low phonon energy in comparison with silicon nanowire. The average phonon group velocity decreases too, and it depends on number of shells of silicon dioxide, and thermal conductivity in nanotubes is lower, so that makes them more promising candidates for application as thermoelectric materials or thermoelectric insulators. What is needs to mention that this decrease of thermal conductivity is in the temperature range from 50 kelvins up to 40 kelvins, so it includes and room temperature, which fact is very important. Thank you for your attention.
Okay, thank you very much for your nice talk. And Professor Kim has a question. I think he can open his microphone and ask himself.
Your structure is very small, so I wonder whether there is any spatial distribution of sound or any standing wave.
Small and what? I haven't listened exactly your question for last phrase from your question. Please, can you repeat?
Yeah. Regarding the spatial distribution, is any sound distribution, speed distribution around your dimension? Yes, for example, around edge, is there any speed difference compared to the central area, or is there any standing wave mode?
You mean distribution of the Phonon modes in geometric, in these geometric structures, how they are distributed.
Yes.
So these Phonon energy dispersions are shown for the waves which are propagating along the axis, because the main thermal flux is along the axis, but not across the layers. So we didn't consider modes which are propagated perpendicular in a cross section of the nanotubes.
Okay, thank you.
Okay, thank you. I think there are no more questions, so we thank the speaker again.
Thank you.
So I will stop sharing. And the last speaker of the morning session is myself. So I introduce myself at the beginning of the morning. So I'm José Manuel Llorens, and I'm working at the Institute of Micro and Nanotechnology in the National Spanish Research Council. And I have also a flash talk, and I will now try to share it with you. Let's see if I manage to do it. Sure, share screen. Okay, we'll try now. Can you see my?
Yes, I see your desktop. Yes.
Can you see my desktop? Okay, because
it's okay.
Okay, this is a very, very short talk. We are targeting to applications on the quantum dot Trig transition, meaning when the wave function of a quantum dot goes from a dot shape into a more complex or shape, meaning that has the shape of a ring, meaning that it changed the geometry and also it belongs to a different topology class. And we have seen this in type 2, indium arsenide, gallium arsenide, antimony quantum dots. Okay, it's the collaboration of 3 universities, Technical University of Madrid, who brought the samples, the Federal University of Sao Carlos, who made the model for the spin, and also our institute, where we have performed the optical characterization and also the K.P and strain modeling. So you can see all the details in the physical review of light. So the main motivation is to find how to exploit this type 2 or this change of geometry and topology. And one of the interesting aspects is to control the G factor of an electron through a gate voltage. So if we have, for example, an electron confined inside of quantum dot that it has a spin, this spin is insensitive to the voltage. but its dipolar magnetic momentum is proportional to the spin through this G factor, and this G factor depends on the wave function of the electron. So it's possible that by applying a voltage to modify the wave function and also the spin. So basically, the voltage acts on the wave function through the Stark strong confinement Stark effect. The spin-orbit coupling couples the spin through the orbital angular momentum or in general orbital degrees of freedom. And through this coupling, we have, in an effective way, coupling the voltage to the spin. So the two key elements are, on the one hand, a high polarizability wave function. And for that is we used indium arsenide quantum dots covered by this overlayer of gallium arsenide and antimony. By changing, for example, the amount of antimony, what we can do is to change from type 1 confinement to type 2, meaning that the electron, instead of being confined inside of the nanostructure, it is expelled out and is confined in the overlayer. This is what we refer to type 2, while this type of confinement is type 1. And it's also possible being in the type 2 confinement, so for a high antimony concentration, to reduce the thickness of this overlayer, and we are effectively pulling down the whole wave function towards the nanostructure. So this allows to make some wave function engineering, but this is static. Instead, if we introduce these quantum dots inside of a pin diode, and we play with the voltage, with the applied voltage, and also with the electric field that the quantum dot is sensing, what we can achieve is an active control, because by applying the electric field, the hole can be either pushed from the bottom towards the top. And as it is in a type 2 biennial alignment, the geometry changes from a ring-like to a quantum dot-like. So then this allows us to have a lot of control on the orbital part. So then the other ingredient is to have atomic spin-orbit coupling, to somehow to transfer this wave, this control on the wave function, the orbital part, to the spin of the state. And for this, we rely on antimony, because antimony is from all 3 fives, basically semiconductors that can be used in an MB chamber or MOCVD to make electronics based on gas technology, gallium arsenide technology. Antimony is the one with the highest spin orbit coupling. And this is basically the main experimental result. And here what we saw is the Sigma splitting that has been recorded for 2 magnetic fields up to 9 and minus 9 Teslas, and comparing the change in the main peak. And this is the feeding. There's a linear feeding that follows the Simon Hamiltonian. And what we found is that by changing the applied voltage, we change the electric field. Also, we suspect that we are moving the wave function in this way. And we found experimentally that we can change the G factor. So we are able to modify the G factor through an external voltage in this type of geometry. I mean, more experimental details and also full details on the theoretical results that support these conclusions can be found in the video and also in the publication, as I mentioned before. So thank you very much for your attention. And I want to acknowledge my grant on the Ramon Cajal program, and also this study is part of the quantum platform on quantum technology, on the platform on quantum technology, so from my institution. So thank you very much. And now if you have questions or...
Yes, I have a question.
Oh, please.
Okay. But perhaps you can try the measurement of AB oscillation in type 2 when hole rotate around.
Sorry? How we measure this? Or
Harmon oscillations, if you apply the magnetic field perpendicular to the quantum ring when hole is in type 2, it has an extra orbit. So hole can rotate around, and the
Yes,
energy
I mean,
well,
yeah, it's that. I mean, to check that we have like an in-plane dipole, what we explore is the Harmon effect with the magnetophotoluminescence. And okay, it's the experiment is in an ensemble sample, so we have only average behavior of many quantum dots, because we still don't have low density quantum dots. But yes, your question is very relevant, very interesting. And what we found is an oscillation in the intensity that is not related with the magnetic brightening. And with a K.P model, I could expect some crossings of the ground states or change in the angular momentum of the ground state that are compatible with this change in the intensity that we found experimentally. Yeah,
okay.
but I mean, if more experiments are coming, then or we could go further. And also, well, if anyone has other questions.
Vladimir had another question. So Vladimir, you wrote this here. Maybe you can ask Jose.
So Jose, very short question. You have extremely highly tunable systems, as you showed.
Mm-hmm.
What are the prospects of application of these highly tunable systems for optoelectronics or for spintronics?
It's more for optoelectronics, because these quantum dots, they have an optical transition, so it's that we can combine modifying the spin of the hole. It will, we expect that this can be transferred to the polarization of the optical transition in a way that we could eventually have a spin photon interface that is very relevant for quantum information technologies. But it's very challenging to achieve all this. But yes, this is the future steps are moving towards that direction.
Okay, thank you.
Because we can combine the optical with the current. Okay, I mean, I have an announcement, so that Pablo will take a picture of all of us. So please don't leave. If you have more questions, please ask now, but please don't leave the session.
I have one more short one, Jose. First
Yes.
of all, thank you for your presentation. It was very nice and yeah, informative. How good can you actually control an experiment? I mean, it's certainly easy to control the electric field, but how good can you control the dimensions and composition of your systems?
Well, this is, as I explained before, it's an ensemble sample. So at the moment we have very low control on the shape and concentration of the antimony, or the amount of antimony. For example, the thickness of the overlayer, this can be controlled quite accurately, but I would say that this is the only parameter that we can address very precisely, because these quantum dots are formed by self-assembling. So, I mean, we have some control, of course, but there is always inhomogeneities, and this is an issue that we want to address with low density samples in the near future.
Okay, thank you.
Okay, thanks to you. So please, can everybody switch on their cameras to take a group picture? Okay, I think it's time to smile.
16 members in the picture.
Yes.
Okay.
It's ready?
It's ready.
Okay. Thank you, Pablo. Okay, I want to thank Pablo because he has been behind the scene all the time trying to fix technical things and so on.
Thank you so
Thank
much.
you, Pablo. You did an excellent work. And thank you, all of you, for attending the session. And now, I think Pablo can open some break rooms. So in case someone wants to keep discussing on the flash talks. And how this works is that it creates like 4 rooms and the speakers are distributed randomly. And from then they can change to other room. Okay. So it's working or?
Yes, I rename the rooms. Yes. Now it's open all rooms.
Okay. Thank you, Pablo.
Thank you so much.